Hey there, my fellow intellectuals. Welcome back to Relearn Probability with me. I was solving a very interesting probability problem the other day. It was posted on a window in Los Angeles where my uncle lives. He took a picture of it and sent it to me. And he's done this to me for the past couple, I think, of years now. There's this store, I don't even know where it is, that puts up problems of math on their window, which I love the idea of. It's just great. They put up a problem that is very easy to state, but it is quite difficult. At least I found it quite difficult to solve. And it wasn't until I thought about it a lot more and realized the depth and the complexity of the problem that it became this challenge. And I just really wanted to solve it. So I've solved it. I will tell you about it. And let's discuss the solution. So the problem says Alice and Bob play a game with a fair six-sided die. First person to roll 6 wins. Alice rolls first, then they take turns. What is the probability that Bob wins? One thing that I hope people are also thinking about is that there's something special about the fact that Bob rolls second, right? Because he doesn't get to go first, he could very well lose on the first roll of the game. If Alice just happens to roll a 6, oh wow, did you just see that? I actually rolled a 6 right there. That's amazing. I actually did not plan to roll a 6 there, but I just rolled a 6. So that could just happen, and Bob never gets to roll this dice at all. He will just never get a chance to roll this dice. So what was the probability of that happening? 1 in 6. Okay, so there seems to be a slight disadvantage to Bob if he doesn't get to roll first. And the answer will actually encapsulate that. So enough talking about the problem and thinking about it. Let's go and solve it with math.
I'd like to first thank past Kyle for getting us started on this problem a few months ago. Yes, I know it was a while since I started this problem, but present Kyle, or future Kyle, depending on your perspective, is here to resume what I started. And that is to show the completion of this problem and show you how you can actually calculate the probability that Bob wins this dice throwing game. So if we look over here, I've written down the probability that Bob wins, and I want to sort of think about this in a systematic way. So let's think about the probability that Bob wins, let's say, on turn 1. So what's supposed to happen on turn 1 if Bob is to win this game? Well, what's first supposed to happen is that Alice does not roll, I'll say A does not roll a 6, right? So if Alice does not roll a 6, that means that happens with a 5/6 probability. And given that she does not roll a 6 and Bob rolls a 6, so Bob will roll a 6 with a 1/6 probability. So Bob does roll a 6. This is the probability that he wins on the first turn of the game, 5/36. But there's no guarantee that Bob will win on the first turn or the second turn or the third turn or even on the 100 millionth turn. There's perhaps a possibility they just keep rolling, not 6s infinitely. Not very likely, but it is probabilistically possible. So for example, on turn 2, what does it look like if Bob would win on turn 2? Well, for him to win on turn 2, Alice needs to make sure she doesn't roll a 6. Bob cannot roll a 6 on his first roll. Alice cannot roll a 6 on her second roll, but then Bob will roll a 6 on his second roll, right? So you can see here we're going to generate a pattern. And I'll do it one more time on turn 3. So let's say here on turn 3. And what I'm doing here effectively is showing that the probability that Bob wins this game is essentially just adding up all the probabilities that he will win on any of his consecutive turns, or any of his turns, not consecutive, but any of his turns from 1 all the way up to infinity, right? So on turn 3, we need to have Alice not rolling a 6, Bob not rolling a 6 on turn 1, Alice not rolling a 6 on turn 2, Bob not rolling a 6 on turn 2, Alice not rolling a 6 on her third turn, but then Bob rolling a 6 on his third turn. And you can see, right, we're just going to be increasing this pattern by sticking 2 more factors of 5/6 on every subsequent turn. So to make this problem a little bit more tractable, what I'm going to do here is I'm going to factor out a factor of 1/6. And so what do we get here? We factor a power of 1/6. For turn 1, we're going to get 5/6 For turn 2, we're going to get 5/6 cubed. For turn 3, we'll get 5/6 to the 5th. And dot, 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 dot. We're going to keep going. What I'm going to do now is I'm going to suggest we do some further rewriting. Now, what do I mean by this? Well, what I mean by this is we factor out a power of 5/6. So what are we going to get? We're going to get 5/36 in front. This will be 1 plus 5/6 squared plus 5/6. I believe that's to the 4th. And then we'll just have all these even powers of 5/6, right? And we somehow need to be able to add up an infinite amount of terms. And thankfully, there are some series that can converge to a finite sum, even if there's an infinite amount of terms. And I'm going to show you this is going to be one of them, but it's not quite in the form that we need it in right now. So what I would like to do in the next step is that let's think about what 5/6 squared is. What is 5/6 squared? That's equal to 25/36, okay? Now, why do I want to write it like this? Because I want to write it like this because then we can rewrite this series in a slightly more neat fashion. So we're going to have the 5/36 in front. Now, 1, right, you can get 1 by taking 25 to the 36 to the 0th power. Remember, any power or any number raised to the 0 is equal to 1. So I'm going to cleverly write this as 25/36 to the 0. And then what is 5/6 squared? 5/6 squared, by definition, that's just 25/36 to the 1. Now, 5/6 to the 4th, that is actually just 25/36 to the power 2, right? So this is just equal to 25/36 to the power 2. That's what 5/6 to the 4th is. And now you can see that I can just rewrite the entire rest of the series in increasing powers of 25/36. Now, why would I want to do that? Well, I'd like to do that because this whole thing right here is a geometric series. Now, a geometric series has a formula for an infinite amount of terms that can give you the finite sum. Basically, what the geometric series says is that if you have a sum going from k is equal to 0 to infinity of, let's say we have some constant a times a power or some fraction raised to the kth power. So this is just equal to, this would just be equal to ar to the 0 plus ar to the 1 plus ar2 plus ar3 dot dot dot. Notice we have that form up here because our a is the common term of 5/36, and then we have 25/36 as the r term, right? Because that's the thing that's always getting raised to a power. So with some clever manipulation of this series, we're able to show that it's a geometric series, and as long as the absolute value of r is less than 1, this has an analytic form. It has an analytic solution, basically. And what this equals is equal to a over 1 minus r. So that is what this geometric series equals in the event that the absolute value of r is less than 1. R is 25/36, and that is less than 1. And so we can apply this formula. And we can find that with this formula, we have 5/36, that's our a, over 1 minus r is 25/36. And so we'll have 5/36 over, let's say, 36/36 minus 25/36, because 36/36 is 1. That's equal to 5/36. And then this is over 11/36. And then we can just do some cross multiplication here. And we'll find that the probability that Bob wins this game is 5 over 11, which is approximately 45%. Now, not 0.45%, but 45.45 or 45%. Now that kind of makes sense intuitively because it is this sort of game of chance, right? Where Bob will, roll a 6 at some point, or Alice will roll a 6. But you have to remember that there is a non-negligible chance that Alice will win on turn 1. 1/6 of the time, Alice will roll a 6 on her first turn, and thus Bob will never have a chance to even get a roll off in this game. So that's the way we need to think about this 45%. It's in the event that in the long run of games, if they play an infinite amount of games doing this sort of simulation, we'll find that Alice will win about 55% of the time because she has the first roll. She will have a chance to win possibly on the first chance. It's not a big chance. It's only a 1 in 6 chance she gets that first roll off to be a 6. But nevertheless, that reflects the probability that she wins, right? So if we think about the probability Alice wins, right? Alice wins. It's equal to 1 minus 0.45, right? Just 1 minus the chance that Bob wins. And it's equal to 0.55. So that's the way to think about this problem. I know it was a bit long. I know it was a little bit tedious to get through all this, but I hope it makes sense in the end because I thought this problem was extremely fascinating. The fact that we were given this sort of easy to understand problem, but then it kind of devolved into this thing where you need to know, geometric series and infinite terms to get to the final answer. So with that, I hope that sufficiently answers the question for you all. I had a lot of fun making this video, even though it took over the course of multiple months. Sorry about that. But if you like this, please like, comment, and subscribe to my channel. If you do, I do like making math videos, I like making physics videos. I like making a lot of different videos that involve math, science, and anything else I find interesting. And so keep watching if you are interested. And with that, I'll see you next time.